Hello, everyone. This is Susong Simon Zhou at Arizona State University. And today I would like to go over the open source dynamic chapter assignment package, DTA Lite, in particular Python code, and with Nesta interface through a number of mini licenses and as a teaching dialogue with Dr. Kefler Augie here, uh, uh, so that we can understand the details and reach the deep understanding of this open source package. In this outline, I would like to go over 4 different parts. The part number 1, we are going to introduce the DTA Lite Nesta very quickly about its modern principle. Part number 2, we'll go to the Python code version 1, in particular 500 lines of Python code to be explained in detail with you. Part 3, I will go over the key visualization feature in Nesta. And part 4, we have Dr. Kefler Augie here to introduce the simple Python version for the automated or connected vehicle simulation. As we can see, as a faculty member at Arizona State University, our ASU try to reach out for the general audience, and we hope many students and citizens can learn this research product and then apply this to solve real world problems. In this part 1, I will talk about the project objective, motivations, and what Nesta and DTA can do, and then talk about the overall design of open source free software package. This is motivated by a number of important open source products. For example, GAMS, General Travel Network Format Specification, and the product of the Life Foundation, which tries to advance with a flexible, efficient support, education, guidance, encouragement through this open source, open standard effort. And in Nesta and DTA package, we want to provide an integrated graphic user interface plus the analysis package so that all the students can learn easily, and will allow the users to visualize time-dependent traffic volume dynamics and with these free education tools. The goal is to make sure all the students can understand the complex decision-making process in transportation planning and optimization processes. The second motivation we have is we need to address a number of existing technical barriers. According to the survey, even a dynamic chapter assignment package is a very important research direction, but the typical DTA package requires too many input data. It might run quite slowly, and more importantly, the model is not clear. So we try to use the GAMS simplified data input from static chapter assignment to build this package. We are going to illustrate how to use the Python code to show you the detailed modeling and use Nesta as a visualization to make sure you can start from the basics and understand the key modeling features. What DTA and Nesta can do, number 1, you can integrate both simulated and observed data into this data hub. Number 2, you can also connect with all the traffic demand and the signal optimization tools together. The typical dynamic chapter assignment package will cover about 2,000 or 5,000 zones, 20,000 links. You could have 2 million or 4 million agents or vehicles. We also have a number of network scenario analysis capability to output in both Nesta and the QGIS or other space and time visualization. As a part of our effort, we always want to say we try to advance the Nesta or the DTA Lite as a prototype for us to show the data hub. In the current practice, we have field data, traffic demand modeling data, dynamic chapter assignment model, micro simulation model, highway capacity manual, land use. As you can see, all the data are connected, but in a very ad hoc way. What we try to provide on the right here, we try to produce simplify the data hub in the middle and then connect the different related data in a much more specific standard format so that we can automate the whole process easily, reduce the time and effort for planners, for engineers. Now I go to a specific about this open source free software package. The Nesta is a front-end GUI. It's coded in C++. Version 0.5 has been the GUI for Transcend's DynaSmart. Version 0.9 at the current stage, we try to support the GAMS data format as an open source data hub. You can import a number of different planning package input to the shape file, and you can also export to the QGIS. The DTA Lite package itself is a C++ version in its own nature. Currently, we extend that to the Python code so that more students can understand this from the deep insight of the data structure. By data hub, what we mean here is we need to start with node, link, different agent as even demand input or the output, the trajectory and the visualization, and the step number 5, you can also incorporate signal timing for the detailed traffic data analysis. The useful material we want to share that with students. We have the DTA Lite software package. We have DTA Lite white paper produced in 2014 by me and Jeff Taylor at the University of Utah. And also we have the DTA Lite source code in both Python version and the C++ version for the larger scale computation exercise. In our DTA Lite package, we are in the middle of macro and micro simulation. Macro level chapter assignment is readily available for most of the regional chapter analysis. DLSim, Sumo are the leading product for micro level simulation. DTA Lite, DynaSmart, Dynasty, and a number of commercial softwares serving at the micro level to connect regional assignment result to micro level simulation. The typical computational cases we are trying to face, in this case, the management statewide model has 20,000 nodes, 40,000 links, 3,000 loans, 18 million travelers, agents in the multimodal network. So we need to use a 20-core CPU structure to solve the traffic simulation and simulation plus assignment iteration. We are use a very efficient open NP structure to speed up the whole calculation. I'm not going to go over all the details, but I think it's very important for us to understand from the very early beginning, we are solving a hyperbolic system of conservation flow with a QK as a flow and a density with a G as a net vehicle generation rate. The typical traffic flow model, we are using a Green-Shields model, and also we are assuming typically the speed is a function of the density. If you're familiar with set transmission model, CTN, this is a one typical calculation scheme inside a simulator. The first step, you try to discretize the network into different links and nodes, and then we are using 6 seconds or 1 second as a simulation time interval. And we can perform this computational step 1, 2, 3. Typically, you calculate the agent speed, you calculate the flow ready to move, and then you transfer the flow from one section to another section. At the last step, we are going to update the prevailing density and then to move the vehicles accordingly to different files. In DTA Lite, the traffic flow model we follow is Professor Gordon Newell's in-curve approach. It's a simplified kinematic wave approach. If you have more interest, you should go to the white paper to read and understand how we propagate the forward wave and the backward wave in a very simplistic but theoretically realistic. Typically, I always want to present the space and the time diagram. In this case, x-axis is the time axis, and the y-axis shows two segments. And we have the traffic congestion from the downstream segment. You can see this is the tail of the queue. We have the green line and the forward wave according to the free flow speed. We have the backward wave and the dashed red line. More details can go into the paper or other traffic flow research. So now, Kevin, are you ready to go over some interesting code with me?
Yeah, I'm ready.
So what are typical questions you might have as a programmer who wants to study the traffic simulation?
Data structure and what are the inputs, and I think how I can simulate the whole process, and how I can code, and how I can manipulate the functions in the simulation also.
Okay, thank you. So now I would like to work with you to go over the step-by-step process. On the left, we try to show the detailed data or the calculation process in our Python code. We do have the class, node, link, network, and we do have the agent to simulate the vehicle trajectory. And we also have the basic network class to show the travel assignment and the simulation process. On the right, as you can see, we have block 1, node and link network data. So we are using the GNS data format. This will be quite straightforward. Number 2, we are prepare the OD demand matrix. This OD demand matrix can be generated from the gravity model or generated from other cell phone-based data sources. Based on network and the OD demand, we are going to generate the agents or the vehicles. In these vehicle attributes, all the vehicles has its own origin, destination, and the path. And then we can plug in item number 3 here with all the traffic congestion mitigation strategies, such as signal control, rate metering, pricing, greens, routing, to simulate them. In this particular case, we are using DTA Lite as a demonstration to show you how we can perform traffic simulation. The output of this could be a widely rich of data set, including the vehicle type, including the trajectory, including emission results. What we want to say here is, once you understand the kernel of this network input, demand input, with the traffic simulation process, you will be able to learn many detailed output as a byproduct of our traffic flow propagation. Kevin, are you ready to go forward?
Yes, I'm ready.
Okay, thank you. So as we show in the previous slide, we try to solve this system equation of network flow balance, capacity constraints. In terms of the mathematic property, we have to maintain for each link the inflow queue and outflow queue. In our coding in the future, you will try to learn here is FFTT as free flow travel time. We have the inflow queue, we code it as a link dot entrance queue. Outflow queue, we code this as a link dot exit queue. This is a pseudo event-based simulation. We do not maintain a vehicle list plus a clock list as other event-based simulation. What we do here is we move the vehicles at each link from the inflow queue or the entrance queue to the exit queue. When we try to propagate the travel time between links, we use the arrival time we use a departure time, and we try to carry out the whole simulation process using a very streamlined queue-based constraint and all the needed simplified car following model or the kinematic wave model. Do you have any question here?
So in the outflow and inflow queue, are you managing the or are you balance the flow in the link with nodes, right?
You have a very good question. So this is a single link structure. For each link, you will store these vehicles in the inflow queue, and then they will send to the outflow queue according to free flow travel time. The flow balance at the node level will be controlled through this outflow queue with the capacity constraint. At each simulation interval, if there's a capacity, we can move from one link to another link. Otherwise, they will stay in the exit queue. I will show more example to you to demonstrate this whole process. So now with this simple understanding, I will go to the part 2 very quickly to talk about the overall dynamic traffic assignment modeling framework, to tell you a little bit more about the agent-based resulting, and to talk about if we try to have different core function, how we consider the value of time. Finally, we have the different traffic simulation model to be reviewed, and then we go to the pattern code. As just you mentioned in your previous conversation, the whole process of the DTA Lite can be decomposed into simulation, shortest path, and this is a simple traffic assignment. So to maintain the flow balance, we have link transfer, node transfer, path processing, and the user decision. The user decision is mainly for this traffic assignment process, and the path processing is going to calculate the shortest path. In this particular case, we are using the label correcting algorithm. Do you have any question here?
In the label correcting is the cost function of the simulation of the the transportation system. So can we assign or design the label correcting in here?
Okay, very good. So in our simplified version of a DTA Lite Python version here, we use the link travel time calculated from BPR function first. But we do also have the shortest path going to the simulator and then produce the time-dependent link travel time. So as you can see from this, inside the simulation, we produce the time-dependent link travel time. This link travel time will be also feed into the shortest path to do the calculation. The shortest path can take the generalized cost. So all the other penalty functions such as penalty, signal delay, or maybe some incentive will be able to go into the extended function, the shortest path for the multi-criteria routing. But in the Python version we have, we'll start from the basics.
Okay.
Then we go to this different traffic simulation model again. So I would like to also start with a very simple way of the point queue simulation. Then we go to newest simplified car following model plus the kinematic wave. So as you can see through this figure, we have entrance queue, exit queue, we have the inflow capacity, we have outflow capacity, we have a 4-lane facility, so that we can use the jam density to calculate the storage capacity. In case we have queue spillback, we can restrict the inflow capacity. So outflow capacity, again, is denoted as a time-dependent outflow capacity, vector or array. And in this way, we can literally code the signal timing or other time-dependent capacity control like here. we have the entrance queue at the least, we have an exit queue also at the least. When we try to move from the cone queue, we need to model the vertical queue. In the vertical queue structure, we will balance the inflow and the outflow capacity. In particular, if I go from the vertical queue to the spatial queue, if the capacity is totally restricted at the exit queue, I will further use the storage capacity to restrict the inflow capacity to make sure we are not going to exceed the storage capacity constraint. I think the next figure is going to show some details around here. We have the node, we have the incoming link, we have the outgoing link of this node. So in every step, go to more specifics. We have the link path and the node path. The capacity constraints are enforced at both ends of each link. At the beginning of the link, the entrance list keep track of the vehicles entering the link, enforcing in the inflow capacity constraints. When we have this link path, the vehicles are moved between the entrance list and the exit queue, and the exit queue keep track of all the vehicles waiting to leave from the link by enforcing the outflow capacity constraint. Then the vehicle will be able to move between the exit queue to the entrance queue of the next link, and this is our node transfer process. And using this node transfer process, we are implementing the flow balance constraint. A long dialogue, do you have any question?
According to last 3 or 4 slides, I understood in here through the inflow and outflow capacities and affecting the flows in a backward way. This allows us to simulate the whole network in multi-agent simulation concept.
Yes.
If I understood correctly. So
yes.
And
yes.
users can or developers can design their networks according to their objectives in multi-agent domain.
Yes, yeah, thank you for your very good feedback here. This is integration of space-time network modeling plus the kinetic wave traffic flow. We have to simplify the whole process so that we can apply this kinetic wave for a large scale network, because a large scale network requires us to calculate the shortest path, and then we perform the shortest path for the different agents. I have to mention a number of a few more details right here. When we have a node as a typical merge node, for example, on-ramp situation here, we need to determine the different rules to allocate the remaining capacity. As you can see, we just show this example. We use a number of lanes as a way to distribute the inflow capacity to the upstream lanes. There's also a very complicated lane demand-based model. I'm not going to the details, but I try to show this picture to raise the awareness. In our mesoscopic model, the important thing is not about the lane changing or coupling. The important thing is to maintain the overall flow balance and the fair capacity allocation to the different approach. In this case, mainland was on-ramp, and by understanding the overall flow balance constraint, we can better reproduce the traffic congestion at a larger scale. As I mentioned, with a diverge case in this slide, you will understand our meso model. If I model everything on the link level, it could be quite complicated. Because if I try to force first in, first out FIFO constraint, ideally, if I have all the apply drivers, they will wait and they execute and then to leave from this off-ramp. In the reality, sometimes there's also aggressive driver will leave from the mainland at the last minute, and it could block the mainland traffic for a certain time period. So how to model those merge and diverge intersection or these are freeway on-ramp and off-ramp within segments, we need a high fidelity traffic network representation. So Kaiser, since you are coming from the computer science domain, you might need to understand the cumulative arrival departure. So we have this cumulative arrival, cumulative departure along the time axis. And then by doing so, using this all the flow diagram, we can understand how you can model the effective green saturation flow rate at an intersection, and then understand the movement specific capacity. And then you can use this structure to simulate the time dependent second by second signal timing to make sure all the signal timing will be consistent with this aggregated hourly capacity. Any further question here, Kaffer, before we move to the actual implementation of Python?
Yeah, presentation and picture, the figures and the information in the presentation is very good for me, and I think I understood most of the things, and so let's go on to the Python code.
Okay, thank you. So now we go to the Python code. So when we go to the Python code, we are going to look at a number of existing source first. First of all, you can go to our GitHub ASU Translation AI Lab. Go to this DTA Lite account. You can go to the source code. You can go to the Python code. We have this version number 1 with all the data input and output and the Python. It's a one single file, DTALite_s.py with the input and output here. In the future, we have the version CAV to be discussed by you to show how we can apply that further for the connected and automated vehicle. Also, I want to show to understand the queue-based modeling philosophy, it's good to read this free open white paper about the DTA Lite simulator. So for the students, you can go to this DTA Lite package. You can click on the code. If you have a GitHub account, you can open with your GitHub desktop, or you can download the zip file. Meanwhile, we also, if you go to the source code here, going to the Python version number 1, I want to just raise your awareness that we have node.csv, link.csv, they are all consistent with our GMS data format. If you go to this upper layer, we have a nested executable. The nested executable, as I want to show you right here in my computer, you can open a network with a node.csv using the GMS data format. And after you open up, you have this node and the link structure. And you can click on the GIS link to show their corresponding information. You can also go to the menu project to show the corresponding node, link, all the different attributes. To save our time, I would like to just go to my local trajectory, my local folder here. This is our DTA Lite Python code. If you have Spider as your compiler, you can open up this Python code. click on the run, you can see we are reading those codes with the 40 nodes, 55 links, and a number of agents, and then we run in the shortest path, and then we perform the traffic simulation to show you how we can understand the inside and outside of the code. For further understanding of the DTA Lite S standing for students, we can also search the DTA Lite S paper, which is published in the Urban Rail Transit Journal for further information. For the students, if you want to learn how our traffic assignment process and the simulation process, you can add your own comments, or you add your own debugging information. For example, right here, from 7 o'clock, CA means cumulative arrival, CD means cumulative departure, and then this is the way we simulate the whole traffic system in one iteration. As other programming guide, you can go to our DTA Lite Python document. We describe in writing to show you all the data input and output. So it's always a good idea for a student to use this document, using this item by item, item A, item B, item C, to understand those details. This is all input and output data format for the node, for the link, for the demand file, and this is a list of the files. And this is our space-time network modeling structure. This is our pseudocode. Finally, we always enjoy using the cumulative arrival departure count to show that we are building our system using these traffic flow fundamentals. Careful, are you ready to go to the implement details of 150 lines?
Yes, I'm ready.
We also have the learning nodes for the DTA Lite version 150 lines. The total number of lines are 500 lines. And we try to show in the first 150 lines the setting of important parameters. And we have a number of simulation settings in terms of the simulation time, assignment, iteration, how we model the different intervals. It could be the simulation interval, assignment interval, the starting time, ending time, converted to the intervals. Into the data structure, in terms of data structure, we have node, links, and agents. We also need to count the cumulative arrival departure. So these are CA and the CD are essential feature of our simulation whole process. So we do use in the future here, use our transportation-oriented coding schema. G means the global variable, and we will try to use our lowercase to show both variables and the data structure. We have a number of classes: classes node, classes link, classes agent, and then finally we are going to output all the trajectory for each agent and then produce the link performance file as our final output. Okay, so now let me go to the Python code to move line by line for a very brief understanding. If you have any questions, please feel free to interact with me, and we are going to demonstrate this whole learning process. Okay. The total number of lines here is about 500 lines. If you go to the very end, yes, we do have the main function. The main function is going to read the input network data. It's going to perform the traffic assignment, mainly using a BTR function for now. And then we have a space-time network-based simulation and the output. Finally, we output two files, link performance and the agent.csv. All these file can be visualized using the Nesta interface. So for the student who wants to really understand this node, link, zone, demand, link performance, agent, yeah, they can use this graphic interface to explore other features. Now I'm just going to the code for detailed understanding. In this first 150 lines of code is mainly about the data structure and the basic mapping between the external input and my internal simulation setting. You can set up the number of nodes, number of links. Since we perform the traffic shortest path, so we have this maximum label as a part of the initialization value. Let's look at this data block. For the simulation time, we have this internal simulation clock. We have this external simulation military time. We always say HHMN or coded in terms of minutes. So we have to convert the external time stamp, external time period into our internal simulation time clock. In this process, we use the 6 seconds as the simulation time interval. 6 seconds equal to 0.1 minutes. You can also use a higher frequency of the simulation interval, for example, second by second. We need to determine the total simulation horizon in terms of interval, because in our signal timing, we have to almost code the second by second green time, effective red time for simulating the traffic management strategy. Starting time, ending time, initialize this first, so that when we read the agent file or the demand file, we will be able to detect what are the planning horizon we have in mind. Number of nodes, number of links, number of agents will be initialized all the way process. Community arrival, community departure to show that overall for the whole network, are we able to discharge all the vehicles. Then for the node, link, agent, we use the list to represent the dynamic memory allocation, and you can depend on the number of nodes and the links you have. Once you use a C++ version, you will be able to more quite a large scale. We have this dictionary to map the node ID to our internal node number, the sequence number. Externally, the user might have the node number such as 10,001. We need to map that to our internal sequence number so that we can have a very compact memory block to store information. This is the agent TD, typically in my code stands for the time-dependent process, because we need to still load 2 million agents in our C++ implementation. So we need to decompose them into these time-dependent intervals so that we can load chunk by chunk of the agent into the network. Kefir, do you have any question about blocks?
Yeah, I think I don't have any question until now. These are the definitions of the variables and for the assignment and the simulations. So I will understand more deeply in the assignment and simulation process, I think.
Okay. Okay.
The usage of these variables.
Yeah. So from line 43 to line 67, we have some data conversion utility function to convert the military time HHAM into our internal time stamp. This A to R is absolute time to the relative time. So we call this as a conversion, a whole. Now, for the node class, we have the very streamlined initialization to initialize the internal attribute of a node. By using this dot initialization, as you can see, we need to assign the node sequence number one by one every time when we read from node.csv. Automatically, we increment this global variable of number of nodes by one. For the link, if you're familiar with the transportation network modeling, we have the essential features of length, typically in km or in mile, number of lanes, free flow speed, capacity typically is the unit of the hour, the link type, and we also have the different facility type or VDF type. VDF stands for volume delay. When we read the data, we are going to read the data directly from the CSV file, and then we pass those attributes into our internal attributes. One thing you do see from here is this capacity typically is coded as a lane capacity. So we need to times the number of lanes to get a link capacity. The free flow travel time, the unit should be minutes internally here. So we use the length either by mile or km divided by the free flow speed is also mile per hour or km per hour, and the times 60 so that we can convert hour-based travel time into a minute-based travel time. In the future, we also show that we are going to do this traffic coding second by second. The offload TD stands for the time-dependent offload capacity constraint, and the size here is the simulation time horizon. Okay? Simulation time horizon. We try to initialize this according to the average link capacity as a default value. We are strongly recommending the student to understand the community arrival, community departure methodology so that we can keep track of community arrival and the departure curve on each link. With this type of CA and CD result, we'll be able to recover the vertical waiting queue, density, offload, and inflow rate. We also count the time-dependent link travel time here so that we can calculate the time-dependent demand. The entrance queue and exit queue are two important lists for each link. So since I enumerate all these important parameters, Dr. Kaffer, which part do you feel that it could be quite important for other students?
I think the cumulative arrival, cumulative departure, and also from node, external from node, external to node. I think to balance the outflow and inflow operations, as you mentioned previous presentation, if I understood correctly, because with these definitions in the assignment and simulation part, probably you will use these variables in that process.
Okay. Very good comment here. Without having the community arrival, departure, and the exit queue, engine queue, we are not simulating the congestion. So, with only link travel time or the link speed, we can only do the shortest path. So that's why, with a strong favor of traffic flow dynamics, we have to rely on those key variables. So we will see these variables again throughout our simulation process.
Mm-hmm.
So since we have the community arrival and the departure at every given simulation interval, at the beginning, we need to reset NOE as a measure of effectiveness. And a key function here, as we also see off-ramp Dr. Baloka has been calibrating DPR function for the large scale network. The DPR function is a long story for the computer science scientists here. Essentially, we are using a coefficient of alpha and the exponent of beta, and use the volume divided by capacity to calculate the actual travel time, actual waiting time. Okay. So with this information, we can go to the class of the agent. DTA Lite is an agent-based simulation. So we are going to stop all the shortest paths into the path-based representation. Essentially, we have the node sequence number, link sequence number, and at each step, we maintain the current link sequence number ID. Basically, it's 1, 2, 3, 4, 5, so that you can see when we are reaching to the end of the destination. If you want to extend the DTA Lite into other multimodal simulation, you can introduce the passenger car equivalent so that you can model a large truck, you can model the bus with a different capacity consumption. Each agent has its own life in the simulation process, so we use this flag. Are this agent being generated? Are this agent already completing the trip? We use this default flag. The departure time for each agent is also given from our either demand file or our input agent list. Before the simulation, we need to initialize the community arrival and the community departure for each link. And then for the agent, we need to initialize the TA, the link arrival time, and the link departure time. And then we are trying to show that as a part of the input and output process. So careful, I think with these first 100 lines, it will be nice for us to further look at the input and output data structure. Yes. Once we are ready, let's try to move on, and maybe we will be able to finish the essential part of.
Okay. Okay. Yes. Yes. The presentation and the presentation of the code was quite straightforward. So thank you for presentation, and I will wait for our next teaching class.
Okay. So for now, I just go ahead to continue. Okay.
Okay. Okay.
So the input node.csv. Each node, we have two zones. We have X and Y coordinate. You can use the longitude, latitude in the future to use the QGIS or other Google Map to display nicely. Link.csv, you have link ID, home node ID, to node ID, direction flag typically is 1. In Nesta, if you have the direction flag at 0, we can model this two-way. Number of links, free flow speed, capacity, this is a link-based capacity, but typically we use a lane-based capacity times number of lanes to get the overall link capacity. The link type can be freeway, arterial. This is mainly for the different traffic flow model or the different VDF, volume delay, alpha and beta parameter. Another key input is our demand file. The demand file in this case is an agent with a different agent type. In the future, you can use passenger vehicle. You can define your agent type as is. So we have the origin and the destination node. We can also provide the origin zone and the destination zone. This is mainly for display those agents data in Nesta to show of agents. We also provide the departure time and the place on.
And I have a question in here. origin and destination node IDs is in the origin and destination zones, right?
Yes, so the zone structure here are mainly used for aggregating the performance. When we try to calculate the shortest path, we still need to go to node from origin to the destination. This is agent-based.
Okay.
Yeah, if we want to show the result, I always want to do that. If you go to the nester, if you click on this agent, you can click on this origin destination. This is the total number of the vehicles. You can see the corresponding travel time, and this is the aggregated process. In nester, we also have this vehicle summary, so you can see the different agent type with the different simulation time, with the different average travel time distance. So the story here is once you have the agent file, you can use the nester to post-process most of the interesting attributes, even including within a day, you have this 95 percentile, 90 percentile travel time. This is due to SHARP2 and O4 project working together with Dr. Hamid Mamasani for both of the. Okay, so with the data input and output briefly being displayed in our last session, now let's go to the second major block of this Python code. So we need to read the data inputs. It's the second block of the data code, including from line 164 to line 300. Okay, so this is the second chunk. First of all, we read all the input data. We open the node.csv using this CSV reader, so we are able to pull out most of the attributes easily and pass that. So this is a node, pass that all the attribute, and then initialize these values, send this particular node into the node list. As we show that internally for the initialization of the node right here, they will automatically to optimize their data block and increment the number of nodes by 1 and create the internal node and the external ID. The second part here is a link.csv. So we read the form node ID, to node ID, the LAN, number of LANs, free flow speed. We are appending this link into node structure. The important thing here is since we are going to do the shortest path, we have still maintained this node list, and then we have this incoming link list and the outgoing link list being stored in this process. For the demand, we just display here. We read agent ID, agent type. This is quite flexible for us to expand this information. And we initialize the starting time and ending time of the simulation horizon based on the demand file. So in this way, when you specify your demand, you can specify your demand from 7 a.m. to 8 a.m. You can also just select another time horizon. Our internal structure will scan the process to determine the initial starting point and the initial ending point. In this second part, the network class is quite important. If I try to teach with the time-dependent shortest path or shortest path, this will be another long class. But for now, let's assuming we understand the node predecessor, node cost, and we are using a very simple shortest path by ourselves. we initialize the node label predecessor first, and we have the SE as a scan eligible list. We scan this link one by one as a first in and first out fashion. And then for each link, if it's still in the SE list, we are put out the corresponding form node. We are obtained the outgoing link with the outgoing link. And then we are further scanned the travel time or the link cost on this link. Then we check the automatic condition. Does the new cost making sense for us to update? In particular, if the new cost is less than the previous label cost, then we are going to update three things: label cost, node level predecessor, link level predecessor, and then we continuously executing this do-while loop. And then finally, after this simulation, we should be able to find the shortest path, origin to destination for each agent. Do you have any question here, Dr. Catherine?
How you preparing demand, or how you define demand? And
yeah, this is a very good question. In our next process here, so this demand is very simple for the illustration. Origin 1 to destination 2. If I open up with our ASU network, right here, this is our ASU network, and you can try to open up, for example, this ocean network. We will be able to show you how to create the different zone and the structure, and then try to obtain the information. So a grade, as you can see, the grade will be used to create the zone. Right here, I have this simple function. You create the zone, and now you can try to turn off the reference grade, and at the node layer, you can try to just add the plus plus. We will be able to show you all these numerical alphabetic grade system. Typically, we call this alphanumerical grade, just like in Excel. A1, B1, C1, A1, A2, A3, so that we can collect the information, production attraction at each node, and then further to produce the traffic flow process. OD demand, as you can see, it can be displayed further in our demand dossier. So I go back to the Python code. Now I go to the third module of this Python code, which is called traffic assignment. Are you ready?
Yes, I am ready.
Okay. So before I go to this complicated code structure, we need to go back to our assignment process. If you still record this modeling framework, we are supposed to perform the simulation and feed the time-dependent link travel time, and then calculate the shortest path. We use the path selection rule to iteratively update it. Right? In the DTA Lite as implementation, in the first few more iterations, instead of using the traffic simulation, we are using the BPR function to calculate the link travel time. In the future, if you see the C++ version, we do use the simulated link travel time to produce all the input. And also, as you can see, this path selection should satisfy a number of decision rules. For example, user equilibrium, system optimal, travel information, or even when you try to model the CAV, you have the informed driver, you have this human driver, you have this system optimal control driver. So this path dimension plus the assignment dimension is very important for us to. So now I would like to just go to the line 298 all the way to 348. This is our agent-based shortest path. Once we have the building block of the shortest path, we will try to calculate for each agent list, and then we will use this random number draw to create each agent at each iteration will be recalculated this shortest path, or will be updated in terms of the shortest path. If you are familiar with our method of effectiveness, I would like to say the MSA method of aggressive average. We are using this k-1 divided by k to select the different number of agents, and then there's only a small portion of the agents at every iteration going to select the shortest path. Otherwise, they will stay on the current path. If you look at the implementation details, this is the iteration number. I is the agent ID. So we are flipping the coins, or you can just see we are just using the symbol of module, okay, divided by, and calculated this corresponding residual to determine which agent will be selected. As a very simple example, if I in iteration 2, I use a 2 finger here, and then when you try to do this divided by or residual calculation, you can see always 1, 2, 3, 4, and one of the agents have residual of the 0, and then by having the residual of 0, we are select this agent for the shortest path updating. Otherwise, when the residual is not equal to 0, we don't need to update them. For each agent, once we try to update them, they have their own link-based sequence number list and a node-based sequence number list. And then we call this shortest path with their origin node ID, destination node ID, the departure time in minute for the shortest path. Once we obtain the shortest path, we are going to convert their current node list into the link predecessor. So in this code, we do a backward searching so that we can grab all the node and the links. And then in the second step, for each link, we need to calculate all the agents passing through this link. And then we got this link volume. Then we are going to use this link volume in our BPR model. So this important routine of find paths for each agent, first of all, involve the MSA method of successive average, and also it involves the shortest path label correcting, and then it also produce the results for the link volume used in the BPR function. That is why understanding all those different connections is very important. Dr. Kaifer, do you have any question in this subroutine?
Without any cost or anything, just finding the shortest path for each agent in that part. The objective.
For the iteration 0 or for the first iteration, we are using the shortest distance, or I will say the shortest distance divided by the free flow travel time. So we are using the free flow travel time. Once all the agents are using the likely shortest path, we become congested. We have the feedback loop. do the BPR to propagate. And then we are going to do this iteratively, typically for 20 iterations to reach the user equilibrium. And the difference between the static travel assignment and our implementation here is that we are doing this agent-based implementation. So the agent could have its own value of time or other attributes based on your extension. In the typical static travel assignment, they perform the shortest path zone by zone. In my standard C++ version, we have both implementation ready. If you're talking about a very large-scale network with 14 million agents, then we have to go to our C++ version to look at the most efficient implementation zone by zone.
Okay.
Okay.
Thank you.
Thank you. So now I think we have 3 more modules I want to continue. Maybe today we can finish this together.
Okay. Yeah.
Traffic assignment is important. Traffic simulation is also important. Once you understand the previous traffic shortest path finding for each agent, then we can go to the assignment process formally. This is the number of iterations. In this MSA or is iterative process, first of all, we calculate the link travel time for each link. We update the cost function, and we are using this independent travel time, in this case, still the static travel time, to find the shortest path for all the agents. Again, some of the agents will have opportunity to be selected at this iteration to select their own shortest path based on the previous travel time. Other agents will stay on their current routes. After this whole process, we are going to re-update the link volume. So you can see this is one of the essential iteration we have. For each iteration, calculate the time-dependent travel time or calculate the static travel time using BPR function, find the path for all the agents, and they update their link volume. So these are 3 major steps are quite important for you to understand. Got it?
Yes, got it.
A common issue or common misunderstanding will be all the agents will find the shortest path every iteration, and then you can see this becomes a game process. All the agents are re-updating, and then they just do this band control. They got this shortest path congested, and then they go to the alternative path, and then they go to the shortest path again. So that's why this whole process essentially is a nonlinear optimization. We need to understand the corresponding user equilibrium, system optimal, and the step size. Otherwise, it's just a one-shot simulation. Okay.
Okay. In here, link list cost. So you are using the travel time as cost.
Yeah, I'm using travel time as a cost. So very good question. I keep mentioning this value of time. Suppose you have $1 imposed on this link, then we need to use your value of time, because your value of time typically is 1 hour equals to $10 per hour or $20 per hour. Then we need to convert this $1 as 6 minutes, for example, and then use a 6-minute equivalent time plus the travel time. Then we can calculate this shortest path with a generalized cost.
Okay. Okay.
Do you have any question here in the assignment?
Yeah, in each link and for each agent, we are calculating the cost, and according to cost, we are making assignment and also calculating volume of the link.
Yes.
Okay.
Okay, now we go to the one of the kernel, one of the most important module here, traffic simulation. This traffic simulation code is related to what we have been discussing a lot throughout the lecture. Okay. Let's revise this a little bit. Outflow capacity, entrance list, exit list. For each link, we have entrance queue, exit queue. We need to move the vehicle from the entrance to exit. And once the outflow capacity is available, we are going to move from the exit queue here, check the outflow capacity, go to the next link. In this demo version, we have not implemented this merge model. Interested readers or programmers can go to our C++ version to look at details. Diverge here is not implemented in the demonstration. So now the key is how we can show the linkage in these 100 lines of the simulation code to the community arrival, community departure, how the waiting time and the queue delay is actioned. Are you ready?
Yes.
Very nice. The global function of traffic assignment starts from line 370 to the line 466. So you can see we are only using about 100 lines of pattern code. We already simulate what is listed. This is a point queue based implementation. Step number one, we initialize the data community arrival, departure, link list for each link. And then we also have a quick initialization for each agent. The input here is the shortest path or this desirable path for each agent and any given iteration. And the second step, we have the time-based loop for simulation. So if you still recall our simulation time interval, so we start from the initial simulation time interval to the end of the simulation time interval one by one. Okay. So step 2.1, we carry over this community arrival departure for the previous timestamp. So in a more direct way, essentially is this is the time, this is a community arrival, this is a community departure. So we carry this to the next timestamp, and then we can start tally all the information. Step 2.2, we transfer the active agent to the first link of their path. Because after we have all the shortest paths for each agent, they need to select their departure time to enter the first link. So you do see we have this time-dependent list. This shows all the agent at the current time and at the current list of the agents. By doing so, we are moving this, for example, 1 million agents, time slot by time slot into the network. We need to make sure all the agents, when they go to the physical link, they should have visible path. And then after that, we will denote this agent being generated, and we can copy their link sequence number. And the first link sequence number being stored here. Then I will put this agent ID, this agent ID or this agent sequence number into our entrance queue of the first link. So this line 304 means we put this agent ID into the first link of this agent path in their entrance queue.
I have a question in here. What does mean feasible path exists flag? Because in the previous part, for the shortest path section, we have already calculated the shortest path for each agent. So in that part, I think we have to ensure the feasible path for each agent.
I will say in the demand file, sometimes when the planners provide the input data, some of the physical paths do not exist. So we need to filter out those broken paths.
Okay.
This is a global arrival count so that we can, this is our CA. So as you can see from our simulation process here, CA is a cumulative arrival. When we try to move from the starting time, 7 o'clock here, CA is a 0, and then we cumulatively adding the vehicles into the network. The CD will be flagged for them to record the leave from the network. Step 2.3, these are link transfer process. This 2.3 is related to the process we have in this slide. Each vehicle, again, check outflow capacity. If the outflow capacity is available, they can also check inflow capacity for kinematic wave implementation. You can also check the storage capacity for spatial queue implementation. If both outflow capacity and inflow capacity are available, we are going to move this agent from the exit queue to the entrance queue of the next link. Once you understand this whole process, so we are performing a do loop for each link. If there are agents in the entrance queue, now we fetch this agent sequence number, and we are going to update the link travel time. Be careful here, this is entrance queue. So for the at the first stage, if you recall that we pull the vehicles into the entrance queue of the link. So this link transfer process is going to first to move from the entrance queue to the exit queue by using free flow travel time. By using this free flow travel time, generalized link travel time. At the step 2.4, at the node transfer process, we are moving vehicles from the exit queue to the entrance queue. For each node, we scan in all the incoming links. For each node, we scan in all the incoming links. On each incoming link, we can check, do we have the outflow capacity available for the exit queue? If yes, we still follow a first in, first out rule to fetch the beginning vehicle at its exit queue and to pull them into the next link. So this is the incoming link index to pull them into the next link of the exit queue. So doing this requires a few more steps of checking. So as you can see, 2.4.1, we check the condition for the outflow capacity. 2.4.2, we need to check, are you reaching the destination? If you're reaching the destination, you don't need to move to another link. When you reach the destination, you should also update the cumulative departure count, just like what we showed here. 2.4.3, we are moving from the exit queue to the entrance queue. And then if we do not complete the trip, we move them one by one. So you do see this is the next link sequence number, is the entrance queue, and then we append this agent ID into this entrance queue. And then we will also update the corresponding TA and the TD. TA as time of the arrival, TD as the time of the departure. For all the vehicles waiting at the queue, these are waiting and called the waiting vehicles, we need to get their corresponding waiting time because they have the actual travel time minus their free flow travel time Then we will add the waiting time into the time-dependent waiting time factor so that we can calculate the time-dependent queuing delay. And then this queuing delay will enable us to update the prevailing density, prevailing delay, and then allow you to do all the real-time now. So again, in this very simple module, initialization step number 1. Step number 2 is a second by second or 6 second by 6 second loop. 2.1, do some quick initialization to carry out the cumulative arrival departure. Step 2.2, transfer the active agent into the first link. 2.3, we transfer from the entrance queue to the exit queue by using the free flow travel time. 2.4, we check available capacity. We will perform the node transfer. For node transfer, we will check the condition of the outflow capacity. We have to check the path ending condition. Finally, we are moved from the exit queue to entrance queue, and then we are going to handle the waiting time statistics. This is our whole process. Every time when we move a vehicle, at the very last step, we will deduct the remaining capacity at this iteration.
Okay. Yes.
Do you have any question here, Dr. Kefler?
I think I understood, and the most important part of the implementation was here. So, and with the well explanation, I think I understood the kernel part.
Okay. Yeah, so I would like to always just add one more note here. For the student who wants to learn this DTA Lite or kinematic wave, they can try to read this paper. They can also just go to our ASU AI Transportation Hub. And if we try to study a little bit further, they can go to the repository. We do have all the wonderful process here for check engineering and analysis. We do have this lesson 1, 2, 3, 4, 5 for different modules. We have a number of undergrad students working with us closely to understand the whole. Okay, last part. This is the end of the kernel. From line 467 to line 559. Are you ready, Dr.
Yes,
Keffer?
I am ready.
Okay, I'm so excited because we are approaching to these last 100 lines. The output here is a link performance. The link performance, as you can see, from node to node time period. In terms of the actual file, if you look at the link performance, so from node ID to node ID, time period, minute by minute, cumulative arrival, cumulative departure. From these, you can derive the density, queue length, the travel time, waiting time. The waiting time is in seconds, depending on how you count their virtual delay. In the next simulation package, I have to go back to here. You can go to the link performance. You can click on this link. You will be able to see these link statistics. You can see this is our inflow pattern or the outflow pattern. Okay, this is the time horizon from 7 o'clock to 8 o'clock. And at least the lower plot, you can try to see the link travel time, or you can try to see the link speed for more information. You can click on this data export to the CSV file for your further understanding of the process. For the students who wants to really understand this time-dependent delay, time-dependent travel time, you can also click on the volume use this Nesta interface to see how the density queue lines are simulated. We do see right here is a traffic bottleneck, and we have a 2-lane facility, 3-lane facility using this configuration. See the total number of lanes, 2, 2, 3, 3. So there's many rich features for us to go back and forth using Nesta to understand the output, using the code to generate the necessary output into the visualization. Okay, so let me go to the coding here. For each link, we convert the internal time interval to the external time in minutes. And then we are using the cumulative arrival, cumulative departure as a mother variable. We can calculate the volume and the difference of the time, difference of the cumulative departure. And then we can also calculate the virtual arrival to get the virtual queue. And furthermore, we can also calculate the waiting time in seconds. The density will be derived using the cumulative arrival minus cumulative departure divided by the number of lanes, because the density has the unit of vehicles per mile per lane. And all of these will be output into the statistics. This, I need to claim that I implement the C++ code from the beginning. I have many students, including the students at ASU, students in Beijing Jiaotong University, and a student, former student like you, and many contributing authors help us to really coming down to this simplified understanding. So we need to learn more along this line. Finally, we have the agent.csv. This agent.csv produce the node sequence, time sequence. So if you recall previously, if I switch back to this agent file, in all given input, this is demand file. We have O and D, we don't have the path. Each agent. And then in the output, we still have O and D for each agent. We have the node sequence as the shortest path calculation. We have time sequence as their travel time on each link. And we have the total travel time. So this is the input. This is the output. What you try to see as a display. If you go to the animation, we move the clock going back and forth, and they can see the traffic congestion. This is just part of the display. So with this, I will be able to just show very quickly. For each agent, I scan the link sequence number, and we produce the arrival time, departure time for each link. We produce their time-dependent travel time. Finally, you can see the solution, the number of nodes, number of links, number of agents, and the CPU running time. Then we complete the whole process. For running the DTA Lite simulation, I think the users can go to GitHub. If they go to the Nesta interface, they can know more about the Nesta visualization. You can go to the our OSINT to GMS to understand how to simulate how to convert the OSINT network into the GMS data format. In the future, I will work with you to show how we can produce the connected automated vehicle simulation based on one of the papers. Dr. Keffer, do you have any questions right here?
The presentation was good, and So for the next steps, we will present a connected and automated vehicles version of the DTA Lite. Yes.
Okay. So as all the audience listening to our dialogue today, I hope you can enjoy our 2 hours in total of the conversation. And we hope that all the students can learn and using our open source data tools, working with scholars like Dr. Augie here to push to the next generation. As a final illustration, I want to show you this visualization feature. At the ASU, we are using the OpenStreetMap to establish the network. Those are the agents we can display. You can switch from the OpenStreetMap base map to the bin map so you can see the satellite image. What we try to describe is mainly the macro network. You can convert the macro network at intersection level to the meso network. Let me switch back here. Macro network, a node is simply described. A meso network, all the turning volume, turning movements. And we can also build the micro network cell by cell. You can see this wonderful OpenStreetMap to the high fidelity conversion. That is why we are looking forward to the presentation by Dr. Augie and to show us how we can use this freely available network from the globe, different country, from your campus, from your city, and then we create the network, we create the high fidelity network, we create the OD demand, we create the traffic signal control together, and then we can simulate through this simulation process, produce some good planning tools for our future generation. Thank you so much, Dr. Augie, and I will see you next time. Looking forward to your wonderful presentation.
Thank you. Thank you so much.
Bye.
Bye.